Hello, this is Professor Arai in section 6.2, distribution of a mean. In section 6.1, we talked about distribution of a single proportion. In section 6.3, we talked about distribution of two proportions. Today, we will talk about the distribution of a single mean. And because this is new, we will introduce a new formula for the standard error. So when you are calculating the standard error for a single mean, you will use the following formula. SE equals sigma over square root of n. Sigma, if you remember, was the standard deviation of the population, and n was the sample size. And like always, the larger the sample size, the smaller the standard error. Now here are some of the notations that we talked about in the past. We used sigma for standard deviation of the population. We used the S when we talked about the standard deviation of a sample. In section 6.1, we talked about the standard error of a single proportion, and we gave it this formula, which is the square root of p hat times 1 minus p hat over n. And today we are learning a new formula, which is the standard error of a single mean, and that's going to be sigma over the square root of n. So let's see an example. Example 1. 78 runners finished the 2008 Olympic men's marathon. The averaging finishing time was 141 minutes. The standard deviation of finishing times was 7.4 minutes. If we were to take random samples of 10 men finishing the 2008 Olympic marathon, what would the standard error of x bar be? So what would the standard error of a single mean? So we will use the new formula that we learned. We learned that standard error is sigma over square root of n. Sigma is the standard deviation of the population, which they gave me in here, 7.4. And n is the sample size, which they also gave me, that's 10. Plug this in your calculator and you'll get the standard error to be 2.3. Now that we talked about the standard error, we will talk about the shape of the distribution. So the central limit theorem for a single mean says if the sample size is large enough, we can look at that distribution as a normal distribution that is centered at the population mean and that has a standard deviation that is equal to this standard error. The new criteria that we need to keep in mind is that the sample size needs to be larger than 30. If you remember, when we talked about the single proportion or two proportions, our criteria were all larger than 10. However, you will see in this section and in the following section, anything that has to do with the mean, the criteria will be larger than 30. So let's see an example. For the class of 2010, the average score of mathematics portion of the SAT is 516. The standard deviation is 116. If we were to take random samples of 50 students taking the SAT, what would the distribution be? The minute they ask me about the distribution, they are looking for a sentence that describes the shape of the graph. It tells me where this graph is going to be centered at and what is the standard error. Either you can write the sentence or you can write the mathematical notation of it. So first you need to calculate the standard error. The standard error is the standard deviation of the population divided by the sample size or the square root of the sample size. So in this case, the standard deviation of the population is 116. The sample size is 50. Plug this in your calculator and you'll get the standard error. Now you will describe the distribution. So as I said, you can use a whole sentence or you can use your mathematical notations. So you can say that this distribution is a normal distribution, meaning it looks like a bell-shaped curve, centered at the population mean, which they gave me, 516, and has a standard deviation that is equal to the standard error, which is 16.4. Now, in most cases, we don't have the population standard deviation. So instead of the population, we will use the sample standard deviation, S. However, replacing sigma with S changes the distribution of the standardized test statistic from normal to t. So you will see every time you change sigma to S, instead of using Z and normal distribution, we will be using something new called T and T distribution. The T distribution is very similar to the standard normal, but with slightly fatter tails to reflect this added uncertainty. I'll show you in a second how the shape is going to look like. It is used when estimating the mean of a normally distributed population in situations where the sample size is small and the population standard deviation is unknown. So if you have a very large sample and you have the population standard deviation, by all means go ahead and use the normal distribution. However, in most cases, we don't have the sigma. So if we have the sample standard deviation instead, then we will have to use the T distribution. So this is a graph that shows the difference between a normal distribution, which is drawn in a black curve, and the T distribution, which you have it in red. So notice how the T distribution has a fatter tails and it shows more uncertainty. Now, the T distribution is defined by the degree of freedom. So remember how we defined the normal distribution by the mean and the standard deviation? The T distribution is only defined by degree of freedom. This degree of freedom is calculated by this formula. So please write it down. Degree of freedom equals the sample size minus 1. Obviously, the higher the degrees of freedom, the closer the T distribution is to the standard normal. So, which makes sense because if you have a larger sample, large enough, it will follow the normal distribution. So let me show you a graph. So here you have the T distribution where the degree of freedom equals 5, meaning the sample was 6. And then you have in blue, you have a T distribution that has a degree of freedom of 15. So the higher the sample size or the larger the sample size, the closer the T distribution will be to the normal distribution. Notice how the blue line is closer to the black line, more than the red line. Let's see an example. Example 3. Find endpoints of a T distribution with 5% beyond them in each tail if the sample has size of 18. Okay, let's do this. But before we go to StatKey, let's just read it one more time. We need to find the T distribution. Specifically, we need to look for the endpoints. Endpoints are always on the scale. And we need to leave 5% in each tail, meaning the midsection will be 90%. So let's go to StatKey. When you go to StatKey, if you're doing any problem that has to deal with T distribution, you will go to the T over here. And the first thing that StatKey will ask you is the degree of freedom. Remember, degree of freedom is the sample size minus 1. In my example, the sample size was 18. So 18 minus 1, it will be 17. Once you enter the degree of freedom, this is what you see in this box. Now, they told me I need to leave 5% on each tail, meaning this would be a 2-tail. And since I need 5% on each tail, the midsection needs to be 90. So once you enter all the information needed, the question was, what are the endpoints? So I need to look at the scale down there. The endpoints are 1.74 and negative 1.74. Let's look at B. Find the area in a T distribution to the right of 2.3 if the sample size is 15. So let's do this. So one more time, you will go to the t-distribution and you will enter the degree of freedom. Degree of freedom is n minus 1 and is 15, so degree of freedom will be 14. And they want me to find the area to the right of 2.3. So click right tail, change the cutoff to 2.3. This number on top here will be the area or the p-value. So the area in this case is 0.019. So I want to stress when to use the t-distribution. As I said, if you have the standard deviation of the population and your sample is large enough, you can go ahead and use the normal distribution. However, in most cases, we don't have the population standard deviation. But even then, we have to have some criteria to use the t-distribution. So the t-distribution is used in one of those two cases. Either that n is larger than 30, then we can go ahead and use S instead of sigma, and we will be using the t-distribution instead of the normal distribution. Or n is less than 30, however, my sample is normally distributed, meaning there are no outliers, it's not skewed, I can go ahead and use it. So when you have a very small sample, you need to make sure that this sample is not skewed or it doesn't have outliers. If your sample has outliers or it's very skewed, then we cannot use the t-distribution and we will go back to the old-fashioned way of finding bootstraps and randomization. So let's see an example about the use of t-distribution. Dot plots of 3 different samples are shown. In each case, indicate whether or not it is appropriate to use the t-distribution. If appropriate, give the degree of freedom and give the estimated standard error. So notice how they are saying estimated, because once you use the S, which is the standard deviation of sample, rather than sigma, then the standard error becomes an estimation. So let's look at each one by itself. Let's look at the first one, A. This is obviously skewed. However, the sample size is large. In this case, this will follow the first option. The sample is larger than 30, so I can go ahead and use the t-distribution. So since n is larger than 30, yes, I can use the t-distribution. The degree of freedom will be the sample size minus 1, which will be 49. And the standard error will be the S, which is the standard deviation, divided by the sample size, the square root of the sample size. So it will be 10.5 divided by the square root of 50. So the standard error will be about 1.485. Okay, let's see another case, B. The sample size is smaller than 30. However, if you look at the sample itself, it's kind of symmetrical. So I can go ahead and use t-distribution. In this case, the t-distribution has a degree of freedom of 8 minus 1, that's 7, and has a standard error that is S 1.25 divided by the square root of 8, and that will be 0.442. Let's look at the last case. This case, n equals 10. It's less than 30. So this is one problem. The other problem, and the main problem, is that I have outliers and it's very skewed. So in this case, I cannot use the t-distribution and I cannot find the standard error using the formula. So I have to go back to use what I learned in chapter 3 and chapter 4 and use bootstraps. But in terms whether I can use the t-distribution or not, as I said, in this case, you cannot use the t-distribution. The next portion of this section is hypothesis test for a single mean. The hypothesis test will follow the same structure as any other hypothesis test. You will have to state the null, the alternative. The only difference now is that instead of using Z, we will be using T. So let's see the formula of T. T will follow the same structure as Z. Remember, Z was statistic minus null over standard error. T will be exactly the same, but this time instead of statistic you will put the single mean minus the null mean over the standard error, and you are going to put the new formula for the standard error. You'll keep the same criteria, is that n needs to be larger than 30, and if that's happening, then I can go ahead and use the t-distribution with a degree of freedom as equal to n minus 1. So let's see an example. So the question is there a 1,000 chips in every bag? A group of kids hand counted the number of chips in 42 bags. Based on what they found, prove that the average number of chips per bag is more than 1,000. So they were challenging this statement here, a statement that says 1,000 chips in every bag. So their sample size was 42. They counted the chips in every bag, and then they found the average of chips per bag was 1,261.6, and they also calculated the standard deviation. And the question is, prove that the average of chips per bag is more than 1,000. Again, the word prove means I need to do a hypothesis test. So the first thing that you need to do is to state the null and the alternative. In this case, the null is that the average is 1,000. The alternative is that the average is larger than 1,000. The next step is testing the conditions or checking the conditions. Basically, you have the sample size equals 42. This is larger than 30, so this is checked. Third step is to calculate the statistic, which they did by finding the average. The fourth step is to find the standard error. So the standard error is S over square root of n, and that's 117.6 over the square root of 42. So the standard error is 18.146. Once you have the statistic and the standard error, you will find T. And T is the statistic minus the null over SE. Statistic is 1,261.6 minus the null average, which is 1,000, over the SE, which you calculated, so you have T equals 14.4. Once you have T, now you can go to StatKey and find the p-value. So we will go to the t-distribution. Degree of freedom is 42 minus 1, which is 41. And this is a right tail test. And I'm looking for t that is beyond 14.4. So this is going to be really, really far. And as you can see, I'm way over here. The p-value is obviously 0. So using the StatKey, we found that the p-value is almost 0 or 0. And based on that, we can reject the null, and we can say that we have extremely strong evidence that the average number of chips per bag in the Chop Ahoy is greater than 1,000. The last part of this section is the confidence interval. Again, it will follow the same structure, which is statistic plus or minus z star times SE. Instead of z star, now we will be using the t star. And in z star, we actually had specific values. But for the t stars, you don't have specific value. You have to find it each time using StatKey, because the t star depends on the degree of freedom. And each experiment that you do has a different sample size. But you need to write it down. Write down the formula for the confidence interval, which is again the statistic plus or minus t stars times the SE. Instead of SE, you can write S divided by square root of n. So let's see an example. Example 5. 11 people were given 46 grams of dark chocolate every day for 2 weeks, and their vascular health was measured before and after the 2 weeks. Larger numbers indicates greater vascular health, and the mean increase for the participants was 1.3 with a standard deviation of 2.32. Assume a dot plot shows the data are reasonably symmetric with no extreme values. Find and interpret a 90% confidence interval for the mean increase in this measure of vascular health after 2 weeks of eating dark chocolate? Can we be 90% confident that the mean change for everyone would be positive? So, to find the 90% confidence interval, we need the statistic, which I'm given, plus or minus the t-star for the 90%, which I'll find using StatKey, times the SE. Again, the SE was the standard deviation, which I also have, divided by the square root of the sample size. And in here, I have the sample size given to me in words, 11 people. So let's do this. So plug in. Statistic is 1.3 plus or minus t-star times SE. So let's find t-star together. So to find t-star, you will go to the t-distribution. You'll enter the degree of freedom. You had 11 in your sample, so the degree of freedom will be 10. And this is a 90%, so I'm going to click two tails, change this to 90. Once you do that, you will have the t-star down there. So this is the t-star, 1.812. 1.3, your sample statistic, plus or minus the t-star, which we found using StatKey, times the standard error, which is the standard deviation divided by the square root of n. Once you plug everything in, you will find that the interval is between 0.032 to 2.568. And we can say that we are 90% sure that the mean change in this measure of vascular health for people who ate dark chocolate for 2 weeks is between 0.032 and 2.568. Since all values in the interval are positive, we are 90% confident that the mean change is positive, which means the vascular health is improving. Next is margin of error. So please write this one down. Margin of error, if you are dealing with a single mean problem, will be t-star times S, which is the standard deviation of a sample, divided by the square root of n. And from this formula, we can conduct another formula for the sample size. So also write this one down. The sample size n equals t-stars times S over margin of error all squared. As beautiful as this formula, there are many problems that we will face every time we need to find the sample size. Now remember, the first thing that we need to find the sample size is the t-stars. But the t-stars depends on the degree of freedom, and the degree of freedom depends on n. So if we are trying to find n, how can we find t-star? So this is the first problem. And to solve this problem, instead of t-star, we will use z-star. The other problem that we might face is this value S. Again, S is the standard deviation of the sample. So if we still don't have a sample, since we're trying to figure out how many cases we need to collect, how can we have the standard deviation? So to solve this problem, we can use one of the following four solutions. We can either use data from a previous study or similar population. We can take a small pre-sample and estimate the S for that sample and use it. We can estimate using the range, which is maximum minus minimum, and divide that by 4. Or we can make a reasonable guess. So the next example, we will use this choice here, and I'll show you how. So let's look at this problem. Suppose we want to estimate the average GPA at a college with a margin of error of 0.1 with 95% confidence interval. How large a sample size do we need? Now keep in mind, GPAs always go from 0 to 4. So we have the minimum, we have the maximum, so we can use the third option. We can estimate the standard deviation as the maximum minus minimum divided by 4. So I can find S to be equals to 1. So now for S, I'm estimating it to be 1. And instead of the t-star, I'm going to use the z-star. And I know for z-star for 95, I can use 2 as an estimate. So this would be 2 times 1 over the margin of error. It's given to me in decimal, so I'll use it. If you plug in everything else in here, you will get a number that is close to 400. So the sample size that we need to perform this experiment, which is finding an average of GPA at a certain college, would require me to collect 400 data from 400 students. So in summary, what do you need to focus on? First, you need to remember that the standard error for a single mean is S over the square root of n. If you have sigma, that would be way much better. The second thing that you need to remember is that the confidence interval for a single mean follows this formula. X bar, which is the sample mean, which you will have, or you can calculate by adding everything and dividing by that number. T star, you have to find it through stat E using the degree of freedom and the percentage of the confidence interval. And then you need to use the standard deviation of a sample and the sample size. Now, to find the hypothesis testing, you need to use T instead of Z, and T will follow this formula. T equals to the X bar minus the null average, so make sure you're using the null average, divided by the standard error. The last thing that you need to remember is that every time you need to use the T distribution, the degree of freedom is defined by n minus 1. And that's it for this section. Thank you.